Dr. Ryan French is a solar physicist, science communicator, and author working at the Laboratory for Atmospheric and Space Physics at CU Boulder. His research takes him all over the world, collaborating with a global community of solar physicists. Ryan also works to share the wonders of the sun and space with the public through social media, museums, and observatories, and on TV and radio. He's the author of 2 books, Space Hazards, which I think he has over there, and The Sun, Beginner's Guide to Our Local Star, with 2 further titles publishing in 2026. Please welcome Dr. Ryan French.
Hello, can everyone hear me okay? Fantastic. I wonder if it might be possible to turn off this first row of lights. If it's not possible, that's totally cool. There we go. Is that a bit clearer now? Okay, fantastic. Yeah, very happy to be here. I actually gave a talk to Denver Astronomical Society 2 years ago. I know Toby was there. I don't know if anyone else remembers being in the room. It was back at your previous venue. It was the week after the eclipse, so maybe people were busy and preoccupied. But today I'm here to talk about a different topic. We're going to be talking about space hazards. What do I mean by space hazards? What are we going to be talking about today? Well, let's try that again. Okay, so we're going to be talking about 3 main topics in the talk today. We're going to be talking about the sun and space weather, which is my field of research. This is my favorite topic that we'll be covering. We'll be talking about space junk, which maybe some of you are familiar with. And then at the end, we're going to be talking about space rocks. That's not just a statement. I'm not just saying space rocks. We're going to be talking about rocks out there in space. Okay, so something very exciting that happened since the last time I spoke to some of you happened just a few weeks after I was here. This was back in May 2024, or the 9th of May, specifically 2024. I remember this day very well. This is my balcony at my office over at the National Solar Observatory and the Laboratory of Atmospheric and Space Physics at the University of Colorado Boulder. We have a lovely view of the Flatirons. And on this day, we were just celebrating our new director. Our new director had just arrived, and we're having a bit of a networking event, some drinks out on this lovely balcony. And we set up a hydrogen alpha telescope to look at the sun. It wasn't for any particular reason, but we were mingling. We had this telescope set up. And then all of a sudden, I got an alert pop up on my phone. It said, X-class solar flare in progress. If anyone doesn't know what that is, it will be explained later. X-class is basically the largest classification of solar flares. We had 19 of these last year, about 50 the year before. And I saw this X-class flare was in progress. So I ran over to this little telescope that we see here, this hydrogen alpha telescope, and I see these bright sort of ribbon-like features on the sun. I said, wow, this is a solar flare. This is happening right now. And over the course of the next hour, 2 hours, we were slowly watching this region on the sun brighten with time. I thought, wow, that's cool. This is the first time I've actually seen a solar flare live with my eye. I spend all day looking at them on my laptop, but all that I do all day is use data from telescopes in space, telescopes in Hawaii. Just to see it with my eye was really cool. Here is a movie of that flare. This is in extreme ultraviolet light from a NASA telescope called the Solar Dynamics Observatory. You can see this bright region down here in the lower right. That is the solar flare. And again, I went home, didn't think anything of it. And then the next evening, something very spectacular happened. Maybe some of you saw this as well. This is what happened the next night. Can I ask for a show of hands? Who here saw the aurora on this weekend? Okay, a decent amount of you. And how many of you saw it from Colorado specifically? Yes. So my wife and I, we ran out to Pawnee National Grasslands, which is a couple of hours drive from here, the darkest skies we could sort of get to. I did an interview with CNN from under the Northern Lights at about midnight, which was really, really fun. There was a group of teenagers, which I think had gone out to camp, just, drinking, partying, doing whatever it is teenagers do. And I sort of sheepishly approached them and said, hey, do you guys know what's about to happen in an hour when it gets dark? We're going to have the best Northern Lights display in like 10 years, and you've got like the best seat in the state. And then over the course of the evening, I heard them like yelling and screaming, and it was fantastic. And it wasn't until the main show was over that finally the people from Denver that sort of caught on that this was happening arrived. But unfortunately, they missed most of it. But really fantastic, really cool to see. It's not usual, of course, to get Northern Lights down here in Colorado. There have been a couple of other instances in the last year where this has happened. Let me ask you this. Who here saw the aurora just before Christmas. It was November time. Okay, and what about in October 2024? Does anyone remember seeing the aurora then? So those are the three big ones that we've had down here in Colorado, which of course is not normal. We don't typically see this, but there's a reason for it that I will explain in a little while. And this whole story of me seeing the solar flare through the telescope and me seeing the northern lights the next day, it reminded me, this is a photo my dad took from the south of England, by the way. He's not a photographer, this is just with his phone, and you can still see those beautiful colors there. So this was a global event. In fact, I have here, this is a view from space of the aurora. So this bright light you see is called the auroral oval. So this is how far the aurora extended. You can see Colorado, where are we? Denver down here. So just below the oval, but not too far, right? And you can see just how far this extended over the UK, where I'm from as well. Very clearly visible there. There's a really fun website where you can go online and log the aurora after you see it. It's called Aurorasaurus. If anyone ever wants to go on Aurorasaurus, this is the website, and this is the output of that. So you basically go on, you say where you saw the aurora, and you say the color of the aurora that you saw. So red or green, or if you just saw like white and didn't see any color, you would put gray, and you can see the clear map here. A good friend of mine who, in fairness, is a professional Northern Lights photographer, he was absolutely gutted that at the time of the biggest aurora, of the last 20 years, he was on vacation in India. So he was really, really upset that he missed it, except he didn't miss it because he managed to photograph red aurora from the Himalayas in India. That's how big this event was. So truly, truly spectacular. It's not all pretty lights in the sky. Northern Lights, they happen for a reason, which I won't spoil just yet. It's coming in a few slides' time. But at the same time that the Northern Lights were happening, GPS started acting really strangely across the world. This is one story that came out in the New York Times. Solar storm crashes GPS systems used by some farmers stalling planting. This is strange, right? This is very odd. How could the Northern Lights stop farmers? This doesn't make any sense. In fact, another article came out a few weeks after this one that said the total financial damage or disruption to the farming industry was $500 million in one weekend. How does this work? Well, as it turns out, farming does not happen most of the time with a person sat behind a tractor. It happens with these huge automated things that are fully robotic, autonomous. They use GPS, these harvesters, they go up and down. And on this night, GPS wasn't working. So that's what caused that disruption. And so this whole story, I jumped ahead of myself a few slides ago, it reminded me of another story that happened 160 years ago, back in September 1st, 1859. This is a story about a man called Richard Carrington. Richard Carrington, if you Google him, this picture will come up at the bottom. It doesn't matter that you can't see it at the moment, because that picture of Richard Carrington is actually not Richard Carrington. There are no pictures online of this man, as far as I can tell. Any pictures that come up, it's normally of somebody else. But anyway, Richard Carrington lived in England back in the year 1859, and he had probably what I would describe as a dream job combination, probably even a dream job combination for some of you. He was a part-time astronomer and a part-time brewery owner. That's what he did. Did astronomy and drank beer, or made beer, right? That was his full-time job. This is his observatory from Redhill, a sort of a city in the south of England. And one day he was observing the sun. He was observing the sun for a not super exciting reason. He was trying to measure how sunspots on the sun, how they rotated at different speeds with different latitudes. Not very exciting. But whilst he was observing these sunspots, he did observe something very exciting, completely accidentally. He noted, whilst he was sketching his sunspot, as you see here, these 4 bright blobs. They weren't flashes, but they were these bright blobs that were sat here in these sunspots. They grew over time, took about 10 minutes for them to appear, and they disappeared again slowly. They moved and sort of changed over this sunspot region. And he did not know it at the time, but he had just observed the first ever solar flare. Or he hadn't observed the first solar flare, it was the first observation of a solar flare. And similar to me, having accidentally looked at this solar flare through this telescope, he went home, not really thinking much about it. And then the next night, something very spectacular happened. This is a comparison, by the way, of that sunspot that he drew back in 1859. This is the one that we had from May 2024, when we had that big aurora. This wasn't quite last week. This is the one in November that caused the big aurora here back in November. Okay, and that evening when he got home, not him when he got home, but that evening, this happened. So there are stories, well-documented stories, in the journals of miners in the mountains of Colorado. So these miners, they went to bed, and they woke up to the sunrise outside of their door. They started getting ready, they walked outside, only the light outside wasn't the sunrise, it was this. And this is the brightest display of the aurora in human history. So here in Colorado, it was bright enough to basically cast a shadow over your head. That's down here, which is basically seen all the way down to the equator. This was in North America, South America as well. Over in Europe, it was daytime, so they didn't see the same Northern Lights display. But over there in Europe, technology started acting really, really strange. The peak of technology at the time was the telegraph machine, and telegraph machines started sending and receiving phantom signals. So ones and zeros and letters and numbers started coming through on these machines, and nobody was sending them. They would unplug the machines, they would get electric shocks, some sparks would fly. There are some reportings of fires breaking out in some of these stations, but those claims are kind of dubious, so take that with a pinch of salt. But again, this made no sense. And Richard Carrington, he put at least the first two pieces of the puzzle together. He said, well, I just saw this flash on the sun. It's a solar flare. The next day, this happened here on Earth. So surely these two things must be connected. Somehow, this event on the sun must be influencing us here on Earth. But how is that possible? There's 93 million miles of vacuum between the sun and the Earth. And how on earth, pardon the pun, could this affect telegraph machines? None of this made any sense. There's a picture of a telegraph machine for any of you who aren't familiar. So what is going on? In both of these cases, we've got the Carrington event, and then May 2024, we have a nice size solar flare, and then somehow something happens between the sun and the Earth, and then we get the aurora and this technology disruption. It doesn't make any sense. But the missing piece of the puzzle is something that wasn't actually verified until the 1970s, and it's something called a coronal mass ejection. A coronal mass ejection sounds like a complicated term, but if you break it down, it's an ejection, so sort of an eruption of mass, of stuff from the sun's atmosphere, which we call the corona. The corona gets its name from the Spanish word for crown. I have a few nice images here for you of some coronal mass ejections. Here's another one from August 2025. That's a really nice one there. Zooming out even further, you can see these structures in just several hours. This is about sort of 12 hours worth of data here, expands to several times larger than the sun in just several hours. So certainly very, very cool. Do I have any more? Yes, I do. This is another movie of a coronal mass ejection, this time from a different vantage point. This was taken by a NASA spacecraft called Stereo. Stereo does not orbit the Earth. Stereo orbits the sun. So this is an observation of the sun here, this tiny dot in the center, and Earth is off the edge of the frame. This is Mercury in the middle. So this is an edge-on view of that coronal mass ejection traveling through the solar system on its way out towards Earth. So really, really cool stuff. This is a very dramatized diagram. The sun is not this close to Earth. It won't be for about 4 billion years, so don't worry about that. But essentially, when this stuff from the sun hits Earth, Earth is protected. We're very lucky we're protected here on Earth by a magnetic field. We're the only terrestrial rocky planet to have this level of protection. Some of the other ones do, but not quite to this same degree. And when this stuff impacts our magnetic field, essentially, it slams into us. It just punches us full force. And when this happens, sometimes, not all the time, depends slightly on the sort of the magnetic configuration of these things, but sometimes the plasma traveling from the sun, this eruption, is able to penetrate through Earth's magnetic field, sort of peels through these front layers. And as it peels through these front layers, it then hits a layer that it can't quite penetrate through, and then flows along the magnetic field and collides with the atmosphere above our poles. And when these high energetic particles impact Earth's atmosphere, that causes them to glow, and that is where the northern lights come from, and the southern lights down south. So when we see the aurora, you're seeing our atmosphere glowing from being just pummeled by these high energy particles out from space. And so the stronger this eruption from the sun, the further through it's able to punch and peel back these layers of Earth's magnetic field. And so when it eventually reaches a layer it can't pass any further through, flows down, and then the further south it will be, depending how strong it's able to punch through. And when this happens, we get the northern lights, as we showed here. There are many other famous sort of solar eruptions. Solar storms is a bit of a colloquial term in solar physics. It doesn't really mean anything super specific, but in general, a solar storm is the reaction of Earth's magnetic field to these eruptions from the sun. Here are a few other notable events in addition to the one from 24 and that Carrington event. In 1921, a solar storm set the railroad on fire in New York, near New York City. In 1967, a solar flare nearly caused the end of the world. This sounds very dramatic, doesn't it? Sounds very dramatic. There was a officer, I can't remember at the moment if it was a nuclear submarine or a ship, I can't remember which one it was, but there was a Cuban Missile Crisis, Cold War, there was a missile-ready ship or submarine, sorry, I can't remember which one it is there, and all of a sudden they lose radio contact with the mainland. And they think, oh no, we've lost contact. Is this a sort of preemptive strike on our communication networks before a nuclear attack began? And so they actually began, following procedure, they began preparing for a retaliation strike to something that wasn't coming. So it turned out what had caused this radio contact to disappear wasn't the enemy disabling communications, it was the sun. And luckily there was one person on board that knew about this, knew about solar flares, said, hey, maybe we should just check and just wait before we get too sort of trigger happy here. And indeed, a solar flare almost caused nuclear war. Back in 1989, there was a very big power outage in Canada, in Quebec. A large area or a larger hydroelectric station lost power for about a day, millions of people without power. What have we got here? 2003 as well, power outages in South Africa and Sweden. But how does this happen? What's going on here? The answer might surprise you. The answer is magnets, magnetic fields. So this eruption, this stuff traveling from the sun, carries with it a very strong magnetic field. And there's something pretty boring in physics. It's not boring, it sounds boring. It's called Faraday's law. And what Faraday's law says, that if you have a conductive material, so a wire, a telegraph pole, a train line, a railway line, whatever it is, if you have some conductive material, if you change the magnetic field over that material, you will create an electric flow. This is the principle behind wireless charging. If you have a wireless charger for your phone or your watch or even your MacBook, this is the same principle there. You change that magnetic field, you create that electric current. And so when you have this thing traveling from the sun, smacks into Earth, it's peeling back these layers of Earth's magnetic field, layer after layer, you're changing the magnetic field around all of these conductive things on the ground. And so all of a sudden your railway lines, your telegraph machines have electricity flowing through them that we didn't put there. It's electricity flowing through them from this stuff coming from the sun. And that's how you get the fires, the phantom messages sending, the disruption to GPS because you can damage these satellites above us, and you can also impact the atmosphere somewhat to change how these radio waves sort of travel through the atmosphere. And all of this together, colloquially, we call space weather, sort of weather in space, right? We're not talking about rain on Mars, right, or snow on the moon. Space weather refers to the immediate environment around Earth and how that reacts to the sun. So I've mentioned some of these. It can impact GPS, it can impact our satellite communication, humans in space, aviation as well, potentially at risk there. So there's a whole different myriad of interconnecting ways that very large eruptions can disrupt our life here on Earth. And this Carrington event back in 1859, this is often considered the worst case scenario. People say, okay, we need to prepare for the worst case scenario. This is about a once in 250 year event. If we had a once in 250-year event, it's not going to be the end of the world. It's not doomsday scenario, but we could lose about 1 in 5 satellites in orbit could stop working or could deorbit and sort of crash down here. We could have regional power outages, so some areas might be without power for days, weeks at a time, depending if you have to fix these transformers. Think back to sort of Texas and that winter storm a couple of years ago and some of the impacts of that. You could have flights grounded for a couple of weeks. Back in 2010, there was an Icelandic volcano and European flights were grounded, right? You can disrupt radio communications, so shipping could be halted. Think of the Suez Canal incident a few years ago and the disruption that caused when ships couldn't go where they needed to be. So a very large solar event is nothing new. Sort of the impacts of that would be nothing new, but would be a collection of all these different disruptions to our lives that is certainly worth preparing for. So how are we preparing for it? What are we doing to counterbalance this risk? Well, there are scientists around the world, forecasters around the world, staring at the sun 24 hours a day, 7 days a week. Up in Boulder at NOAA, there's the Space Weather Prediction Center, for example. This is a picture over from the United Kingdom. The UK Met Office has a Space Weather Prediction Center too. The US military also has one, and South Africa has one. Sweden has one, and there's a few around the world of these forecasters. And these forecasters literally just watch the sun all day, waiting for something to happen. And then when something does happen, they issue out alerts and warnings to power companies, airlines, satellite operators, who can then take action to minimize the potential risks. But my feeling is you don't just have to wait around for this once in a 250-year event. Smaller events can happen too. And if you are anyone working in these very niche fields, you care about those small events too. We used the example of farming a little bit earlier. This is just a scale. We rank these events on a scale of G1 to G5. That one we had in May 2024 was the first G5 we've had since 2003. So it really was a very large event. And an example of why we don't just care about the big events, we care about those little events too, is back in 1973, there was a sort of early space station called Skylab. Skylab was in Earth orbit. Astronauts went on board Skylab, they did experiments, and Skylab was meant to last for several years up in orbit. But back during this time frame, solar activity was much stronger than expected. It didn't just cause Skylab to fall out of the air, right, all of a sudden, but slowly over time, you have solar flares. These solar flares, they hit the upper atmosphere of the Earth, they expand that air pressure up in space, just a teeny tiny bit. So very slowly over time, your satellite is experiencing more friction than you intended it to. So as you add more friction slowly with time, you start losing speed and your satellite slowly deorbits. And this did happen with Skylab, which no longer is in space. You can actually now visit it in the desert in Western Australia. So Skylab fell out the sky, not just from a single flare, but slowly over the year, more flares than expected. You cause this thing to crash land into the desert. Here's another example, this one from 2022, SpaceX. So a private corporation launching a bunch of Starlink satellites. I'm sure you're all familiar with Starlink. Maybe you find it frustrating the way it gets in photographs all the time. It's really annoying in radio astronomy as well. But the Sun did a good thing. Back in February 2022, they launched 60 Starlink satellites during a solar flare. You know, private companies, they don't follow the same sort of care and procedure that NASA does, for example. NASA would never do this, but they launched 60 satellites and 40 of them crashed. Because this air was slightly thicker than they expected, so they didn't make it up into space. So you don't just need to worry about these once in 250-year events, but if you work in these fields, you need to be considering this all the time. Not quite all the time, because the sun does not consistently churn out these things all the time. The sun actually follows a cycle, an 11-year cycle of increasing and decreasing activity on the sun. So this here on the left is an image I've split down in two. On the left, this is the sun in 2019. So you notice an absent of any of these bright points. These bright points are active regions. These are the spots on the sun where we get solar flares and eruptions. And on the right here, this is the sun in 2025. So you can see here the difference between the sun at solar minimum, as we call it, and solar maximum. And the number of these bright spots on the sun follows an 11-year cycle. And you can see here on the left the last few years. We've just passed the end of 2025. This is where we are. So we are currently in solar cycle 26, as it's called. You can see 11 years ago, back in 2014, we had a very weak solar cycle. And 11 years before that, 2003, the cycle was actually a lot stronger the cycle that we're having now. So if you are a satellite operator, SpaceX, for example, you don't need to worry about these things all of the time, but around solar maximum, you certainly need to care about these things. And there's another reason why we should care about satellites falling out of the sky, and that segues us into our next topic, the topic of space junk or space debris. This here is a very simple plot. On the bottom here, this is the year, starting 1957. And this is the number of rockets, what have we got? Payloads and rocket bodies in space. So these are things that we have sent to space deliberately. So sort of rockets, the things that attach to your rockets. As you may or may not know, once a rocket gets its object into space, its satellite or whatever, the rocket doesn't come back down. The rocket just stays floating up there, useless, uncontrollable, but floats around. And you can see a real boom starting around 2020. This is where the onset of SpaceX and other sort of large, or Starlink, I should say, and other large networks have come online or started to come online. And with more objects in space, we get more space junk. I alluded there that not everything in space is necessarily useful. Here at the bottom, this red color is all the useful stuff we have in space. These are our payloads. And you can see the rest of this is stuff we don't want. This is payload fragmentation debris. So these are bits and pieces that have come off the rocket, payload debris, rocket debris, all of these things. None of this is controllable. None of this is useful. It's just up there orbiting around in space. And so what, you may say? Why does this matter? And that's a very, very reasonable question. The reason it matters is that although the space around Earth is very, very big, right, certainly very expansive, the areas around Earth of usable orbits is actually surprisingly not big. There are three main orbits that we have here on Earth. We have low Earth orbit. This is stuff that is very close to us, not really that far above the atmosphere. The International Space Station is down here. This is where you send all of your cheap stuff. So if you don't want to spend a lot of money sending stuff up here, you send it down there. And there are advantages, there are disadvantages. It's cheap to get there, you're low to the ground. The disadvantage is you can't see a particularly large area because you're so close to the ground. This is a very busy area of space. Then out all the way at 36,000 kilometers, what's that in Mars, about 22,000 miles, something like that. We have another very special orbit. This is called the geostationary orbit. And the reason this is very important is up at the geostationary orbit at this very specific height, your satellite will rotate round the Earth once every 24 hours. So this means that if you're at this height, your satellite will always stay above the same location on Earth. So we could have one up above us right now. It would stay there forever if it's in this orbit. And all the area in between we call medium Earth orbit, and you can see isn't as populated as these two outer areas. But unfortunately, space is busy, and space is getting busier, as I showed you, and so collisions do happen. This is a picture here. This is a crack, not life-size, thankfully, but it was about 1 centimeter wide, this crack. And if I asked you, where's the worst place this crack could be? It's there. This is the window of the International Space Station. So there are astronauts on board. Imagine you're sleeping in a floating tin can flying around the Earth, and you go and you see this in your window, not a particularly reassuring sight. Thankfully, it was filled in, it was repaired. But this is on the window of the International Space Station, and they think the thing that caused this impact was a fleck of paint about the size of a grain of sand. Why does this happen? How does this happen? Well, the International Space Station is orbiting around Earth in low Earth orbit. Things there are traveling at about 17,000 miles per hour. And things can go in any direction, right? So if you're traveling at 17,000 miles per hour and you hit a fleck of paint that's traveling 17,000 miles per hour the other direction, you're essentially hitting that thing at 34,000 miles per hour. So even a tiny fleck of paint that doesn't weigh anything, right, can cause cracks in glass that's a couple of inches thick. So collisions do happen. This is another example on the opposite end of the spectrum. This is a European Space Agency, so an ESA weather satellite. You can see it's huge. There are some people standing down here. This is about the size of a bus. This was launched in the 80s, I believe, and it wasn't up there for very long at all, and it stopped working. And the reason it stopped working, as it turns out, is it was hit by some tiny pieces of space debris, which hit it in some critical systems, and now it's no longer operational. And the reason why this is a problem is no longer do you now have the piece of space junk that hit this. This itself is now space junk, right? If your satellite gets hit by space junk, it will become space junk. And then if your satellite then hits another satellite, that becomes space junk. So it's kind of like a feedback mechanism here, right? Especially if this thing were to crash into sort of 1,000 pieces. You now have a cloud of debris that is flowing around space, just hitting more and more things as it flows. And the idea behind this is called the Kessler syndromes. This was introduced by a scientist called Kessler back in 1978. He first postulated this might be a problem one day. He said, debris hits a satellite, as we've said, that satellite breaks into hundreds of pieces of debris, and all these continue to hit debris, and it goes round and round and round and round and round, until eventually low Earth orbit becomes completely impassable, right? You have a cloud of stuff floating around all of Earth, and you can't send anything through it. You can't send anything up there. This is a real possibility. Thankfully, at the moment, unlike most problems at Earth, where it feels like we're saying these things are going to happen within the next couple of decades, this is about 50 to 100 years away at our current rate. So hopefully by then, we can find a solution. How do we do that? How can we find a solution? Well, there are a few different ways that are already being tested to fix this problem of space debris. The first of these is the easy one: satellite monitoring and avoidance. What does this mean? Well, most satellites that are in use have fuel reserves on board. So there are large stations on the ground that monitor the locations of tens of thousands of these tiny objects in space, even ones that you're not using, right, or ones that you can't control. And so if you see something is going to collide with your satellite, you can give it a maneuver and move it about 100 meters. That's sort of the margin of error there. Move it out the way, you're safe. The International Space Station does this about a dozen times a year, at least. And that rate that they have to do maneuvers every year is just increasing, increasing, increasing. The next one is end-of-life planning. Plan something for your satellite at the end of its life. Don't just let it die and stay there in perpetuity where it risks being collided with and causing a cloud of debris. So what does this mean? Well, if you're in low Earth orbit, this means, unfortunately, you have to deorbit your satellite right into Earth's atmosphere. It burns up in Earth's atmosphere. You don't have to worry about it. This sounds great in theory, right? It burns up, it's not a problem. There have been some concerning reports, as you can maybe imagine, from the last year even, to say, okay, what happens to Earth's atmosphere? What happens to the air above us if we burn thousands of sort of heavy metals, thousands of satellites worth of heavy metals over the next few decades? And as you can imagine, not great, not great, but the timelines of that problem are much longer than the timelines of this problem. So as is always the way, right, that's sort of been kicked a little bit further down the road. And if you're up in geostationary orbit, where you have this orbit where you're staying above the same location, instead of coming back down, you kick it out in the other direction. You don't have to escape Earth's gravity or anything like that, right? Just go a little bit further such that if something does happen to it, then it's not going to disrupt the orbit that is useful down here at geostationary positions. And then the third one, which is the cool one, right, the science fiction sounding one, is cleaning up the debris in space, which we've started to do, which is really epic. This is a artistic rendering of a concept mission called Clear Space One. This is a UK space agency mission. This has happened. So this is just a rendering, but this has happened. Just a single test of one single satellite being scooped up by this giant claw. So you imagine you have this giant claw, almost like a claw machine, right? There's a large thing orbiting around the Earth. It's out of control. It's not controllable. You claw onto it. You hold onto it and you say, right, we're kamikazing down into Earth's atmosphere, and you both burn up together. So this is useful for that larger stuff you want to get rid of, but can't get rid of that smaller stuff. So there have been some other experiments with sort of nets and magnets and other things like that. All early development, but showing promising science. When things do enter the atmosphere, as I said, they will burn up. That friction on the satellites just heats these things up to enormous temperatures, so they do burn. This is the re-entry of a telescope a few years ago. This was planned, so end-of-life planning, burned up in the atmosphere, and this is what it caused. So really beautiful stuff. This is actually the image on the front page of my new book, Space Hazards. And yeah, really epic, like loads of tiny, tiny little meteors entering Earth at the same time. Meteors. Oh, that's a very well-planned segue into our third topic of this talk, where we're going to be talking about meteors. So meteors, as we know, shooting stars, are the burn-up of rocky debris as they enter Earth's atmosphere. Here's a nice picture, a painting from back in 1868. This meteor was painted by several artists from across several different regions, so this was a very large event that was observed around that time. Here's another very famous meteor strike. This is back in 2013 in Russia, in Siberia, in a town called Chelyabinsk. And this is the first meteor that we have footage of, basically. Back in 2013, Russia was a bit ahead of the times in terms of dash cams. Everyone in Russia had dash cams back in 2013, I think before they did in Europe or out here. And this large meteor entered the atmosphere, burnt up, and it was caught by many different angles. It was very helpful for scientists. I gave this talk back in the UK in September, and someone who was Russian came up to me afterwards and said, "Oh, I want to comment on you saying that everyone in Russia has sort of dash cameras." I said, "Oh yeah, why do they have dash cameras?" And the answer was, you can get your driving license by bribing the official. So insurance companies make sure you have dash cameras because no one can drive in Russia. Is the answer that they gave me as a Russian. Don't know if I believe it, but that's what they told me. But certainly a very interesting event scientifically. In terms of human safety, human lives, this did not make its way to the ground, so it didn't burn up. It burnt up in the atmosphere before it got to the ground. Here's another angle there of it burning up as it's gone. This is sort of the trail that's been left behind. So it didn't make its way to the ground, but it did cause a very large shock wave in the atmosphere. This is a very loud bang. Everyone heard it at the same time, a loud bang. Everyone rushes to their window, looks outside, what's going on? Where unfortunately, that shock wave ripples through the town. Everyone's staring out the windows. Every window shatters in the city. So there was over 1,000 hospitalizations of people from just broken glass alone. So that was really the only injury, was everyone staring by the window and getting these getting injured in this way. But where do meteors come from, right? Where do they actually come from? Meteors, meteor showers, we have these clusters of meteors several times a year, the Geminids, the Lyrids, all of these things. They typically come from either asteroids or comets. Not the asteroids or the comets themselves, but as a comet travels through the solar system, it leaves behind a trail of debris in its wake. That tail, it leaves behind stuff. And so every year when Earth orbits through that same place in the solar system, it moves back through that same debris field. So really when we see shooting stars, especially during these meteor showers, they're not necessarily these things hitting Earth. It's these things in space that are relatively stationary, and we're sort of just sweeping into them. So sort of the opposite way around. And rarely, some of these events also can come from sort of asteroid debris left behind too. What is a meteorite and what is a meteor? There is a very specific scientific difference. It's a meteor if it burns up in the atmosphere, and it's a meteorite if it makes its way to the ground and makes a crater, or very near the ground. You would still sort of consider it a meteorite, even if it doesn't cause like a big crater. But if it sort of levels a large area from that shockwave, you would probably still consider it a meteorite. Here we go. Object burning up. Object that makes its way to the ground. And there's a third definition, a meteoroid, which is an object in space before its fate has been decided. It's not collided with the Earth just yet. Some people, scientists, travel the world in search of meteorites. They're very helpful scientifically. Some people can be far luckier, or unluckier, depending how you see it. This is Ruth Hamilton, a woman from Canada. This was just a few years ago, back in 2021. The story is quite comical. She reported laying in bed, hearing this loud bang and this crumbling of her ceiling. The dog started barking. She thought that someone was breaking into her home. Sort of in a sleep-dazed state, she jumps out of bed, grabs her phone, calls the police, and then sort of looks around, is coming to sort of consciousness, and looks on her bed, and she sees, oh, it's just cut off. You can just about see it. It's cut off by the bottom of the zoom here. But this large object, there we go, thank you, sat on her bed on the pillow next to where she was sleeping. So she was on this side. This object lands on the other side. And police officers came round. The police officer was the first to correctly say, I think a meteorite has fallen through your roof. And he was correct. It was verified scientifically that this is a meteorite. Here she is here holding it. There's another story back in 1954, this time in the US, in Alabama. This is Anne Hodges, and she's the only person on verifiable record, at least, to be hit by a meteorite. A meteorite, as she was laying on her sofa, taking a nap. These people always seem to be sleeping when this happens. This time it was in the middle of the day. She was on the couch downstairs, and a large crash came. A meteorite came through the ceiling, hit her large sort of radio console that was next to her, sort of ricocheted off that onto her sleeping body. So it did have some points of contact with the roof, this radio console, before ricocheting onto her. Here she is with the hole in her roof, some police officers sort of in disbelief. There's a very graphic photo that you can look up of her in the hospital. She has these huge sort of black bruising all the way on her side. So she was taken to hospital. There was no internal damage. It was all sort of exterior stuff. Here she is in bed recovering with her meteorite. Unfortunately for her, a bit of a legal battle ensued following this. Meteorites, as you can imagine, are very rare, so they're very expensive for collectors and the like, right? Collectors want to buy these things. And so you might think a meteorite landing in your house is like gold falling through your ceiling, right? These things are worth hundreds of thousands, millions. But unfortunately for Anne, is she did not own the house, she was renting. So her landlord sued her for possession of this meteorite. There was a long legal battle. And in the end, Anne did win custody, but there was a custody. Maybe like the fact that it hit her, right? The fact that it hit her maybe gives her a bit of weight in the argument there. But there was some some cooperative agreement, shall we say, some agreement that if she ever sold the meteorite, she would have to give the landlord some percentage of that sale. But it was up to her if she ever sold it. And good for her. I don't know if it was out of spite for the landlord. She never sold it. She, and I quote, used it as a doorstop for many years. And at the end of her life, she donated it to the Natural History Museum in Alabama, where it still is there today. But how can we prepare for these asteroids, right? Is there anything that we can do? How do we stop these things happening? Well, it's very difficult to stop them happening, although I will share a slide in a couple of moments. But the first thing that we do is we assess the danger. There are not thousands, but hundreds of these different stations around the world or different research groups that in some way or form try and forecast or observe or detect asteroids. And when these are measured, when they're found, we calculate the probability of them hitting Earth. We calculate the damage that would be expected if it did hit Earth based on the speed this thing's moving, the size of this thing, and we give it a scale on the Torino scale. So from 0, nothing's going to happen, all the way up to collisions that are very certain. Number 10 here, it says, a collision capable of causing a global climatic catastrophe. Such events occur once per 100,000 years or less often. So the first thing that we do is measure that. Another very cool event, this is the largest event on human record on this Torino scale, reached a scale 8, also in Siberia. Seems weird that Siberia keeps getting meteor impacts, but you consider how big it is, not necessarily surprising. This event was back in 1908, ranks 8 on the scale, as I said. It's about a 50 to 60 meter size asteroid, entered Russia over the atmosphere, and it leveled 2,000 square kilometers, which is about the size of a very large metropolitan area, I think sort of metropolitan New York, completely flattened all these trees. And I think this photo was taken a long time after, years later. You can see some trees starting to regrow, but this whole thing is leveled. Unfortunately, during this event, there were casualties. About 3 men died who were foresters out in the woods at this time, sort of wrong place, wrong time. We can imagine if this happened over a large sort of city, which is very unlikely, as we say, but you can sort of imagine what that damage would be. But much larger events than that, 9, 10 on the Torino scale, very, very rare. This is a meteorite crater out in Arizona, the Beringa crater. Has anyone been there? A few of you here. And in this case, This is the crater here, and just how lucky we are. The crater here, look how close it came to hitting the visitor center just next to it. Sorry, that's a very bad joke. But how do we prevent these things? We talked about how we can prevent space weather, how we can prevent space junk, but what can we do about space rocks? Well, here's a little bit of a story here about this satellite here, or this asteroid here on the right. This is an asteroid called 2024 YR4. This was discovered in January 2025. And at the time, it was given a fairly decent probability of hitting Earth in a couple of decades' time, about 3 or 4%, I believe. And as more measurements came, as we sort of refined our estimates, this gradually, the probability of hitting Earth decreased, to where now the probability of this thing hitting Earth is 0, but it may still hit the moon in 2032 or something, which would be very cool to see. So that first thing that we can do is monitor and surveillance. Know what we're dealing with, when we're dealing with it, potentially, right? If you think it's going to hit Earth at a specific time, maybe a few weeks out you can predict where on Earth it's going to land. You can start thinking about evacuation and things like that. Here we go. Sorry, that's the story I jumped ahead there. February 25, we found this 100-meter wide asteroid, and by the end of the month, just a few days later, the probability had fallen down to 0. So that's great news. The next thing we can do, asteroid redirection. Again, this sounds super sci-fi, but this is something we're actively doing at the moment. In 2022, not sure why that random M's there, the NASA Double Asteroid Redirection Test, which stands for DART, a bit of a forced acronym, throwing a dart at an asteroid, but it successfully impacted and changed the orbit of this asteroid here, Dimorphos. So in theory, this is a proof of concept where if you have enough time, again, we're talking lead time of years, we're not talking lead time of weeks or months, but if you think an asteroid has a good chance of hitting Earth, you send something heavy, as big a satellite as you can muster, and sounds really fancy, redirection test. All that means, just drive into it as fast as you can. That's what a redirection test is. And you just want to bump that asteroid just a tiny, tiny bit so that you change the angle of its direction very slightly, such that over the years that follow, it no longer hits Earth sort of as originally predicted. And that's where we sort of are. That's all we can do in terms of asteroid at the moment. But what's next? What else is there out in space that can potentially harm us? Well, those three main things I discussed are sort of the lifetime scales, I like to call it, the things that we have to think about and make progress towards in our lifetimes. But over scales of hundreds of years, thousands of years, tens of thousands of years, there are other things in space that can cause havoc for us here on Earth. Things like gamma ray bursts or nearby supernova explosions. Again, we're talking millions of years for those things, but those can, in theory, damage our atmospheres in ways that could cause Earth to be very difficult to live on, right, for a few years. But again, this is millions of years away or even longer. Rogue planets. It doesn't have to be a planet. This could be a rogue star or a rogue black hole, just something that's traveling out there in space by itself that comes close to our solar system. It's not going to collide with Earth. That's not going to happen. The chances of that happening are so astronomically small. But if something passed by the outer solar system, even at a distance, I don't know, about 1,000 times greater than the distance between the Earth and the Sun, all the way out past a very large cloud of rock in the outer solar system called the Oort cloud. If anything passes nearby out there, we might not even know about it if it's a large planet. But what that can do is that can disrupt with its gravity all of these rocks that we have sitting at the outer edge of the solar system, such that 1,000 years later, the inner solar system gets bombarded by asteroids. Anyone alive then wouldn't even know what caused it. They would just know all these asteroids suddenly bombarding Earth. This happened a bunch of times in the early solar system when a bunch of planets in the solar system changed order over the first billion years or so. But again, something we don't have to worry about for a very, very long time. Something we will have to worry about with certainty, but not for a while, is 4 billion years from now. The Earth, or it's not the Earth, the Sun will expand into a red giant. It's not going to explode, it's not going to go to a supernova, but it will very slowly, over about 1 billion years, slowly expand, get hotter. It will swallow Mercury, will swallow Venus, and Earth will become uninhabitable. So again, very long way away, but something that, if we're still around in 4 billion years or whatever, fragment of something that used to be a human is around in 4 billion years, they will have to worry about it. I think it's going to be on a Tuesday, in case you want to stick it in your calendars. 5 billion years from now, another certainty, the Andromeda galaxy, which is our nearest galaxy, I'm sure many of you have seen Andromeda through a telescope, will collide with the Milky Way, which is our own galaxy. These galaxies will merge, again, over very, very long timescales to form one mega galaxy, which will be called Milkdromeda, is going to be the name for that one. Again, sounds dramatic, a galaxy colliding with another galaxy. Is the sun going to collide with another star? What's going to happen? The answer, probably not. The probability during, a galaxy of 250 million stars, billion stars, merging with another galaxy, the probability of any two stars colliding is about 40%. So again, all these stars, billions of stars, the chances of any single collision is less than a coin toss. So that's not going to happen. But as I said, these stars fly nearby one another. You're kicking up all this stuff. Supermassive black holes in the center of the Milky Way are going to merge. They're going to spread. Most stars actually will end up as a part of this supermassive black hole. That's the most likely scenario for Earth or the solar system, is it probably will end up in that supermassive black hole or could get ejected from the galaxy completely. But again, the solar system will be dead by this point. Not our problem, right? I think this one's on a Saturday if you want to schedule that one in. And finally, we finish the talk here. Tens of billions of years from now, hundreds of billions, thousands of billions, we'll have the heat death of the universe. So at this point, there'll be no stars, there'll be no planets, there'll be nothing except individual atoms floating there in space. But again, I wouldn't lose sleep over that one. And so to conclude, astronomy is beautiful and fascinating, as I'm sure you all agree. There's many reasons we should research astronomy just for intellectual curiosity, right? But also, many astrofields do have these real-world implications on Earth. And as scientists learn more about these topics, we're becoming ever more prepared, and the risks from the sun, the risks from asteroids, the risks from space debris are lowering with each year that passes, which pleases me to say. So with that, I thank you. I welcome any questions. I do have a few copies of some of my books out the front at the end of the meeting if anyone's interested in buying a signed copy. Happy to do that. But for now, I welcome any questions. Thank you.
So does atmospheric resistance clean up space debris?
Depends what you mean by clean up. It gets rid of it, it will burn it up, but then you have those burnt up elements sort of becoming gases in our atmosphere. So it cleans up any sort of solid mess, but leaves behind this gaseous mess.
And I mean, what kind of time scale are you talking about for, if there's a pink chip or a full satellite or whatever for atmospheric resistance to make a difference?
Yes, so it depends on the orbit. The actual burning up process, it's exponential, right? So you can imagine you're sat up here, say the Earth's surface is down here. You're sat up here, there's very little resistance. Let's say there's a solar flare, this atmosphere expands just a little bit, right? So now you slow down a tiny bit and now your orbit is sort of here instead of here. If you have a few different solar flares, such as Skylab, this happened over the course of a year. It's slowly deorbited and deorbited. But the further down that you get, it accelerates, right? So then the easier it is to accelerate it even further. So the actual burning up process is the same speed as a meteorite, right? This thing enters the atmosphere 17,000 miles per hour, burns up in seconds, right? Or 10 seconds for these really, really large events. So it depends on your height. The Skylab was very high up. Took a year to deorbit, but those Starlink examples that I showed, they burnt up at the day of launch. So that was just a day, a single flare, where they didn't quite make it up high enough, and they slowly deorbit until they burn.
Hi, I have a comment and a question. I'm finding so much that I learned while watching Star Trek, the original series. One of your comments about being able to, I guess, move an object before it hits the Earth, that was one of the themes of one of their episodes where they tried to push an asteroid, which I found fascinating. My question kind of relates to that as well, because in some of the literature I read, being a big Trekker, if a spaceship travels through space and it hits something that small, is that going to be feasible? Can we logistically overcome those hurdles to prevent what happened to that glass? In this case, it would be, the skin of the spaceship,
Yep.
Especially at those, exceptionally high speeds. What are the practical ramifications, I guess, of space travel with the debris?
Yeah, so the first thing, which is sort of a simple answer, is just have massive shielding around it. So the space station, other than the windows, does have this massive padding, and that absorbs most of these fragments into them. They can go a little dense, maybe an inch deep, but if your thing is a foot, 2 feet wide, that's not a problem. You can't do that with Windows, of course. That's where we are at the moment. There are scientific concepts of maybe using magnetic fields to clear, to deflect at least anything that is magnetic. So that could include paint flecks, debris of satellites, and so on. So if you're traveling at speed, you can deflect with a magnetic field and not take that impact head on. But that at the moment is sort of developmental and not been done in reality just yet.
Hi, I'm John.
Hey, John.
That was a cool Star Trek episode. I thought of that too. The Fabrini, that asteroid deflector, that was a good one. Is the work you're doing at LASP and everything, is it safe from this anti-science nonsense that's going on now in the cuts, or are you guys on the cusp? This is valuable stuff.
Yeah, it's turbulent. So my research at LASP, so I research solar flares, which we mentioned, these large explosive events on the sun that can trigger these eruptions. So I research the onset of solar flares. So essentially the first stage that causes the flare, the eruption, travels to Earth, the solar storms. A lot of my funding, or all of my funding at the moment, comes from NASA. I was quite fortunate to be awarded a 3-year grant at the beginning of last year, 25. So I had that 3 years of funding safe. As for NASA's future, it's a bit more optimistic this week than it was about a month ago. So in the president's budget, which came out last summer, the proposal was to cut NASA heliophysics, which is anything to do with the sun, by 55% cut. The National Science Foundation as well, they do a bunch of ground-based solar observatories. It was similar, about 60% cut. And that was sat on the cards for all of last year. So NASA last year didn't really issue any new grants or anything like that. So some people have had to leave the field because funding lapsed. But as of last week, some good news, Congress rejected that president's budget. So that president's budget was rejected, and the new proposed budget is about a 5% cut in real terms. So 5% maybe might seem bad in a normal year, but this year 5% sounds great. We'll take 5%. So that's the proposed congressional budget. They haven't voted on that. They vote on that at the end of the month. And the hope is when that goes through, there'll then be some, sorry, I'm standing too close to the speaker. There'll then be some certainty on NASA's side whether then have the ability to start releasing new mission calls and all these things like that. So hopefully last year was kind of sucky, but hopefully will be better moving forward.
Did any of that impact Artemis 2 or Artemis 3?
So funnily enough, when the president's budget came out, all of the science was cut, but the exploration stuff was boosted. So, and it wasn't quite boosted as much. The whole budget still came down about 40% in the president's budget, but the current administration really want to go back to the moon. They really want to go to Mars. They're kind of interested in that sort of exploration, be the first kind of beat China to the moon again kind of thing. So there's funding there. Yeah.
Would it be anarchy if we changed the scale? So Carrington event could be a G7 instead of a G5? Because if you think about it, if the telegraphs were doing what they were doing back then and everything was hotting up, it seems to me with that technology, with just via wires, and now we have all these cages and stuff that we could concentrate radio waves or whatever. We weren't there then, but it wasn't underreported. It's just there was not that many people. It just seems to me it hit dead tangent to Earth. Not that a G5 has to hit dead tangent to cause the northern lights, but it just seems to me maybe 1859 was a little bit bigger than we think without knowing.
Yes, one thing we can measure with certainty. So we obviously didn't measure the size of the solar flare at the time. There have been estimates to say what that was. One thing we were measuring back then, although not with as much accuracy as now, there are these things on the ground around Earth called magnetometers, and they measure Earth's magnetic field. And during a solar storm, you can literally measure on a graph the change in this. And so we did measure that during the Carrington, the physical change in the field. So that gives us some estimation. But as you say, we had a G5 in May 2024. 5 is the highest scale. The Carrington event, probably 5, 10 times stronger than that. So at the moment, we have a scale of 1 to 5, caps out at 5. Things can be much stronger than 5. NOAA, the Space Weather Prediction Center, did announce last year that at the end of the current solar cycle, which peaked last year, so we'll be coming out of that in the next 3-4 years, at the end of the current solar cycle, they will redevelop that scale. So that is something that is a problem that's been acknowledged and they will be changing.
All right, we'll go online real quick. Ron Rannick, you had a question?
Well, comments. First of all, Ryan, great presentation. Thank you very much. The topic is of interest to me because I've long been a fan of space weather because it ties in with astronomy and ham radio. For those who are curious or would like to track space weather, at least if you have an Apple platform, an iPad or an iPhone, the App Store has an app called Solar Monitor, and I keep that one on my phone and get regular alerts, mostly M-class and stronger flares. Interestingly, a couple of years ago, the Denver Astronomical Society was doing an outreach event out near Morrison, and we've been doing that one for the past few years, and they asked us to bring solar telescopes to set up. So I brought a hydrogen alpha scope and a white light solar scope and had just set them up and was looking at the sun, and things looked good. Stepped away from the eyepiece for a moment, and then a couple minutes later stepped back, and I noticed in the hydrogen alpha scope from one of the sunspot groups a really, really bright spot. And I thought, oh boy, we got a flare going on here. And about 2 minutes later, I got the alert on my phone through that app that an X-class solar flare just happened. So that's the second time I've seen a solar flare in hydrogen alpha light. It just happened to be in the right place at the right time. So it's called Solar Monitor. Don't know if there's a similar app for the Android platforms, but it is available for the Apple platforms. And you mentioned the Chelyabinsk event in 2013. That was Valentine's Day here in Colorado, and it was Friday morning in Russia. The estimate was that the chunk of asteroid that entered Earth's atmosphere was about 10,000 tons. Most of it was destroyed in the airburst, as you noticed, and about 2,000 pounds of fragments have been recovered on the ground. The biggest was about a 1 meter diameter chunk that was recovered from a lake bottom, and some may remember seeing pictures of the hole in the ice on the lake. And about 6 months later, they recovered that, and that was about 1,400 pounds. But other pieces were recovered off the top of the snow and in the snow just days after the event. Thankfully, nobody was hit by that, but as you did note, quite a few people were injured by flying glass from the airburst and the shock wave. And this is one I was hoping you might touch on, is the idea of tracking asteroids that are on a trajectory for impact with Earth. And back in 2008, the what is now known as the Alma Ceta meteorites were produced by an asteroid that was identified in space and tracked and predicted to hit in Africa. And indeed, it did produce meteorites on the ground in Sudan. And those are called the Alma Ceta meteorites. Very strange meteorites. They're almost like a jumble of different types of meteorites. Polymic urolite and a few other things are in some of those meteorite fragments from that one. I think there have been one or two others since then where they've confirmed an asteroid in space, tracked it, and then it collided with Earth. Fortunately, they're not very, very big, but the technology is fascinating with this stuff. So thanks again for a great presentation.
Well, thank you, Ron, for that context. Yeah, thank you. The app Solar Monitor is a good one. Space Weather Live is another app. But as Ron pointed out, if you're live observing with H-alpha and you see a flare, you're actually beating the satellites by a couple of minutes. So it's always cool when you get to see that.
I seem to remember a few years ago that the Russians or Chinese intentionally blew up something in space. I can't remember if it was a laser or what they used. I wondered if you could comment on that and what happened since.
This was the Chinese. And they did this, they claim, as a test to make sure they could the way they framed it was, oh, we just want to make sure that if one of our satellites is tumbling out of control, we can destroy it. But really it was a show of force to say, hey, we have the technology to knock stuff out of the air. It's actually this spike right here. So this spike right here was from a single event. It was a ballistic missile from the ground. China went and exploded one of their own satellites, like a weather station, that caused a huge cloud of fragmentation. And there are some simulations you can go online and watch, an artistic rendering of a computer simulation, where you can see the cloud of this thing spreading through and then hitting some other things on the way. Yeah.
I have a question.
Sorry, Wari. Hello.
Hello. You mentioned satellites hitting each other and ways of preventing collisions. I had a conversation once with a friend who told me that there isn't really a set standard or convention for ways of preventing those collisions. So, it's really some poor fellow in SpaceX who gets 100 emails a day. I'm not sure if that's true. I was wondering if you knew.
So, the whole of Earth orbit is kind of like the Wild West. There's very little regulation. So there's a United Nations Office of Outer Space Affairs. They try to regulate some of this space junk stuff, clean up your mess, don't deliberately break things up, don't shoot your satellites with missiles, kind of thing. But none of that is enforceable. So the role of, monitoring a satellite and moving the satellite falls pretty much to each company or agency. And some of these might outsource these roles. But in terms of SpaceX, for example, that is, I don't know if they have an internal monitoring system, an external monitoring system, but it very much is an alert, flags up, this is a risk of colliding, you need to move this within the next day. And it really is like a reactive thing. You don't get days and days of build-up. Every day there are maneuvers happening, especially with SpaceX. They have thousands of satellites, more than any other company. So it really is the Wild West, completely unregulated.
Along those same lines, I thought it was really interesting when you showed the picture of the crane-like device picking up an old satellite to move it out of the way. I'm curious what you know about how small of objects we can track, and if there's any plan for smaller things. I mean, if a fleck of paint can do that kind of damage, what would a small pebble do? And is there any plan for those smaller things?
So your small pebble and above size, that you're then talking complete destruction of your satellite, essentially. Imagine a pebble traveling at 17,000 miles per hour, you'd completely obliterate the thing. In terms of tracking, we can't track microscopic stuff, but we can track anything on the scale of sort of tens of centimeters. So 10, 20 centimeters and above, we can track. So pebble size, we're not there just yet. Flecks of paint, we've got no chance. Yeah, game over.
So I'm wondering about probability, or how predictable is it for predicting another solar minimum, such as the Maunder minimum and the associated, little ice age?
Yep, great question. So I mentioned the sun follows this 11-year cycle, which we can see here on the left, and what the gentleman at the back is referring to. Back in the 1600s, there was a period where we entered solar minimum, and then we didn't go up again. There's a bit about 50 years where it stayed flat, nothing happened, and then came out. This is called the grand Maunder minimum, the grand minimum. There were some scientists at the time of the last solar cycle, so back here, seeing this massive dip from the previous cycle. They said, okay, I think we're heading into another period of ground solar minimum. But the scientists that predicted that were expecting sort of a decay down further. So given this cycle has been much stronger, it seems unlikely that we will be entering another Maunder minimum, and it seems we're going to continue this 11-year cycle at least for a few more decades.
In the middle here, with the addition of Vera Rubin and its commissioning in the next couple of months, what kind of things can amateurs do with that massive data or our own equipment to help, provide extra data in this field of asteroid monitoring and collision potential avoidance?
Yeah, interesting question. So Vera Rubin is this new telescope that's been built. There's some fantastic images that come out. I expect there might be the development of some sort of citizen science projects, which are sort of these online platforms where amateurs can go online and look through the data and help scientists. So I imagine there might be some citizen science things coming out very soon. If a interesting object is found, let's use Dry Atlas as an example, right? That was found by professionals, and then amateurs got loads of really cool photographs that were really helpful and scientists there, just as an example.
Hey, sorry. Hi. So you mentioned that there's people watching the sun and tracking all that sort of thing. And it sounds like you're working on this. To what extent do we have the ability to predict a week, something earlier, like we have a weather report for the sun to have the solar flare come along?
Great question. And it varies with what exactly that you're talking about. So we have on the sun these sunspots, and these sunspots, these dark patches, many of you probably have seen sunspots through a telescope. You can look at the sunspot and you can basically assess its complexity by looking at it in white light, by looking at its magnetic field. And so from looking at its complexity, you can kind of make like a probabilistic forecast of, hey, this looks like it might produce a solar flare on average once a day, or on average once every 5 days, for example. And so we sort of have that probability thing. Similar to maybe earthquakes. You can look at the San Andreas fault and say, hey, this is a very nasty earthquake fault. This might produce an earthquake every 100 years. This small one might produce a little one that will however so long. So the flare itself is probabilistic. We can't say when a flare is going to happen. But when the flare does happen, and we see that flash of light, we can measure, like I showed you some images of, the eruption, that coronal mass ejection traveling away from the sun. And that's when the prediction part comes in, where we look at that imagery, we measure the speed, the angle, and then we try and assess, okay, how long before that hits Earth, and what will the impact of that be at Earth? And so the very fastest events, it's 24 hours. So you get 24 hours notice from that flare on the sun to, okay, everyone go outside, there's going to be northern lights, or, prepare your satellite operators, you might have to move some stuff around last minute. But slower ones, that can be 4 days. Yep. Okay, thank you very much.
Thank you. That was fascinating. We appreciate it. He will be here. Feel free to drop by and ask him questions afterwards.
I've got free bookmarks.
And free bookmarks.